In today's video, we're going to be moving on from finding maximums and minimums, which is what we've been doing for the past few videos, right? And we're going to look at some different ways that derivatives are helpful. And so today we're focusing on two different things, differentials and marginals. And I want to start with marginals. Marginal is a term that we use a lot in economics when we're talking about cost, revenue, profit. A lot of times we'll look for what's my marginal cost, what's my marginal revenue. What am I talking about with that? Well, if you look up the definition for marginal value, you get this: the change in a value associated with a specific change in some independent variable. Well, what word hopefully stuck out to you? Change. That means marginal value really is just a rate of change. How does one value change as you change the independent variable? Well, remember, if I'm talking independent variable, I'm talking about my x value, right? So when I say the change in a value, what value am I talking about? The y value, or the dependent variable. So all a marginal is just a rate of change. How is your y value changing as you change your x value? So this is equivalently just a rate of change. It's just a different way to say it if you're talking about a specific context, like economics. Well, what do we call an instantaneous rate of change? A derivative. Remember that all a derivative is just an instantaneous rate of change. So in this chapter, when we talk about marginal costs or marginal revenue, we're really just talking about a derivative. Marginals equal derivatives. So let's look at an example of this, okay? Let's say I have a function with the specific demand function P equals 200 minus 3x. Okay, why is this a demand function? Because x represents number of products we can expect to sell, and P represents the price. What do we set the number of products as? If I change the price, I'm going to sell less products. If I want to sell more products, I need to lower the price. We okay with that? Okay. So what if I asked you to find, this is example 1. Okay. What if I asked you to find the marginal revenue? What am I talking about? Well, like we said, marginal, if I use that word marginal, I'm really just talking about a derivative. Find the derivative of what? Of my revenue. So I want the derivative of my revenue in terms of x. Okay. Well, that means I need to come up with a revenue equation. I need a revenue equation in terms of x. Okay. Well, this relates to the football ticket problem that we talked about in our last video. What's my very basic revenue function? With just a simple business model, your revenue can be calculated by just doing the number of products you sell times the price you sell them at. Right? If I sell 10 baseball bats at a price of $5 each, I can just do 10 times 5 to find that total revenue. Okay. Of course, this is the same kind of problem that we ran into in 2.5. I can't take a derivative of this if I've got two different variables, but remember, my company already has this demand equation to kind of show how the price and the number of products I sell are related. So using that, I can plug 200 minus 3x in for P, distribute, And I now have my revenue equation all in terms of x. That means I can go ahead and find my derivative, right? Remember, dr over dx is just the derivative of r. And so I get 200 minus 6x, just using the power rule. So there's my marginal revenue. Now, some questions might have you find the marginal revenue at a certain point. So what all that means is that they'll want you to find the marginal revenue at a specific x value. To find that, find your marginal revenue, and then just plug in the value. So let's say for us, right? What's my marginal revenue for x equals 50? No, that's too big. Too big. Let's just do x equals 10. Okay. What does that mean? X equals 10 means I'm going to be selling 10 products, or if we're working with thousands, 10,000 products. But 10 represents the number of products I want to sell. Okay. Well, since I'm looking for the marginal revenue at x equals 10, I'm going to be using my derivative. So all I would need to do is just plug this into the derivative. R prime of 10 equals 200 minus 6 times 10. And I get 200 minus 60, which is 140. What does that even mean? What does that even mean? So, remember, all a marginal is a derivative, and all a derivative is a rate of change. How is this changing? So what this tells me is that my revenue is increasing. Revenue is increasing by $140 per product I sell. If, of course, this is at a specific point, right? So this is if I'm selling 10 products. Oopsies. If I'm selling 10 products. Okay. So that's what this 140 means. My revenue is increasing, right? It's my change in revenue as I increase the number of products I make by 1. Okay, but this is specifically at 10. So this rate of change wouldn't apply if I was producing 5 products or 20 products. It only applies if I'm selling 10 products and I want to increase it to 11. If I want to increase it to 11, I can expect to see a $140 revenue increase. And same thing if I go the other direction. If I decrease it by 1 and only produce 9 products, I could expect to see around a $140 revenue cut. Okay, so that's marginals. All marginals are just derivatives. Okay, so now let's talk about this idea of differentials. And to understand differentials, we need to review some notation. Okay, let's consider a function y equals f of x. Okay, y means, my output equals some function of x that depends on x. Remind me, what's the difference between this notation, dy over dx, and this notation, triangle y over triangle x? Well, we just saw this notation with the lowercase d in this previous example. This just represents the derivative of the function. Okay, and if you remember right, the derivative, the reason why I'm still kind of using this notation over here is because the derivative is a rate of change. It's just an instantaneous rate of change. Okay, it's an instantaneous rate of change, which means dx is theoretically infinitesimally small. It's infinitely close to 0. Okay. Well, what about this notation? delta y over delta x. Well, if you remember, delta just means change, right? And it can be any change. It doesn't have to be small or large. It can be any change as long as it corresponds to whatever my change in x is. Okay. How do I calculate this? Well, if you remember, right, this is just, right, you subtract whatever your two x values are to get your change in x. And then if y is a function of x, then you can plug those x values into your function to get the corresponding y values, and then you'll subtract them like that. Okay. So when I use that lowercase d, I'm really talking about the derivative, right? It's linked to what the derivative is. But if I use this triangle notation, I'm really just talking about what's my difference between the y values, or what's my difference between the x values. And I find that just using subtraction. Okay. So how do these relate to each other? Well, this d, lowercase d concept is what we call differentials. And it turns out I can use differentials in order to estimate changes, to estimate specific changes. Okay, and here's why. So if I come over and just look at my differentials, I can move things around and rewrite this as dy is equal to f prime of x times dx. You okay with that, right? All that is just multiplying both sides by dx. So I can rewrite my differentials that way. But how does this relate to my delta y, my delta y and my delta x? Well, it turns out if delta x is relatively small, as long as delta x is relatively small, we can actually use the instantaneous rate of change to help estimate. Actually, let me just write it this way. Then it turns out the instantaneous rate of change is going to be approximately what my average rate of change will be, as long as delta x is relatively small. Well, what does that mean? That means that if I know my delta x and I know my derivative, I can use the derivative to estimate, let me be clear, we're estimating here, what delta y is. So that's where differentials can be helpful. So let's look at an example of this. What am I talking about here? Let's look at an example. So let's say I've got a function, f of x equals 7 over x to the fourth. Remember, I can just rewrite this as 7x to the negative fourth. Okay. And I'm going to give you two more pieces of information. First of all, we're going to be looking specifically where x is equal to negative 1.8. Okay, that's where we're specifically looking at, x equals negative 1.8. And I'm also going to give you a delta x value. I want you to notice what's true about that delta x value. Would you consider that relatively small, 0.1? Yeah, that's relatively small. So what does that tell me? That tells me I can use the derivative to help me estimate what delta y is. Okay? So, but here's where we got to be careful. There's two parts to this problem. There's one part where it asks me to actually calculate delta y. What is delta y? I'm not estimating delta y here. I'm calculating delta y. So because this function is relatively simple, I don't actually need to estimate. I can calculate delta y without it being too difficult. How do I do that? Well, remember, delta y is just equal to my change in x values, or my change in y values. y2 minus y1. But what's y2? What's y1? What's y2? What's y1? Well, x equals 1.8. This piece right here, this represents my starting x value. Or another way to write that is, this is my x1. Negative 1.8 represents my x1. So, if I want to calculate y1, y1 is just f of negative 1.8, right? It's just whatever my output value is for negative 1.8. But what about y2, right? So let me just be clear. Y1 is equal to f of x1, which is negative 1.8. But what about y2? How am I supposed to find y2? Well, y2, of course, is just, oopsies, no. y2 is just, of course, the function value at x2. But what is my x2 value? Well, that's where I can use this. My change in x is equal to 0.1. So how much am I moving? If I'm starting at negative 1.8, this 0.1 tells me I'm going to go up by 0.1. I'm going to change by just 0.1, and by a positive 0.1. So that means my x2, that tells me my x2 is equal to negative 1.7. Do we see that? How I just went up by 0.1? And because I went up, because I added 0.1, my number got less negative. So that means y2 is just f of negative 1.7. So there's my y2, minus my y1. Okay. And when I calculate that, I can go ahead and plug in those values into my function, and I get 0.83811 minus 0.66682, which is equal to 0.17129. So there's my actual change in y. No estimation needed. That's my actual change in y based off of my delta x, based off of the given delta x. But now, it wants me to find f prime of x delta x. Why? What does this do? Remember, this estimates delta y. This estimates delta y. Okay, well, if I want to do this, that means I need to know what the derivative is. Okay, so let's come back up here. My derivative, just using the power rule, I get negative 28x to the negative fifth. Or negative 28 over x to the fifth. Right, so there's my derivative. And then, so with that in mind, what I'm going to get here is I'm going to get what, negative 28 x to the negative fifth. But what am I plugging in? Since I'm estimating delta y at this specific starting point, I'm plugging in negative 1.8. So that takes care of this piece. But then I still need to multiply it by delta x. And of course, my given delta x is 0.1. Okay, so to estimate delta y, we take the derivative, plug in my starting x value, and multiply it by my delta x. And if I do the math here, I get 0.14818. So what does this tell me? This tells me that my delta y is approximately 0.14818. So, of course, so you'll notice you get different values because, once again, this second process is just an estimation. Okay, so that's differentials. So on your homework, you'll see some problems where you're working with differentials, but with profit, with revenue, with cost. You'll also see some problems where you don't actually need to estimate, and it's going to be asking for dy. If it's asking for dy, then there's no estimation necessary. You're just going to take the derivative and multiply it by whatever dx they give you. Okay, and then you'll also see some problems with talking about marginals. And what are marginals again? Marginals are really just derivatives. All we're doing is just finding the derivative. So good luck with the 2.6 assignment. Let me know if you have any questions, and I'll see you in the next video. Thanks, guys.